In this lecture, I want to look at the other attributes related to NMR spectroscopy. Um, that is the attributes of the data that you acquire when you do an NMR spectroscopy experiment. And so let me just lay out the four attributes. And so number one is going to be the number of signals. This is sort of a table of contents for the previous lecture through the next lecture. So number two is the chemical shift. And that was the last lecture. We'll touch on that just momentarily here. Number of signals we'll touch on during this lecture. The integration we'll touch on this lecture. Okay, and I suppose I should throw in the confirmation lecture. So this is splitting. No, we'll do splitting next lecture. Splitting is also called multiplicity. So this is sort of, as I said, a table of contents, the four attributes of NMR data. So as you're trying to understand, inspect, gain insight from NMR data, this is what you're going to be kind of sifting through and searching for. So let's start with the first one, which is the number of signals. Okay, so the number of signals is the number of peaks in the NMR spectrum. And what this does is this tells us, or corresponds to, the number of unique chemical environments present. The number of unique chemical environments present. Okay, so let's do an example of one. What I want you to do is sort of predict how many 1H and C13 signals for the following molecule. I'll wait just a second. We'll head over to the next page. So you can pause it here if you want to work through this. But otherwise, if we look at this molecule in more detail, by drawing maybe the Kekulé structure, okay, so what we have here is a molecule with 3 carbons. There's no symmetry that allows for the carbons to be identical. So the number of, or in identical chemical environments, the number of C13 signals is going to be 3. We could think of this as, I'm going to go lowercase a, lowercase b, and lowercase c. 3. Ca, Cb, and Cc. All 3 of those carbons are in different chemical environments. For example, if you look at Ca, it's a CH3 group. Okay, now I know there's another CH3 group, which is carbon C, but carbon C is directly attached to an oxygen, whereas carbon A is separated from that oxygen by a CH2 group. Now I know the CH2 and the CH2 of carbon B and the CH3 of carbon C are both attached to an oxygen, but the CH2 is different. It's got a carbon attached to it. So we have 3 unique chemical environments. That means we expect 3 signals in the C13 NMR spectrum. Now what about 1H? Well, it turns out for the most part that H atoms on CH3s are the same. Okay, so what we have here is A. I'm going to label all of these as HA. Okay, so all three of those HAs are in the same chemical environment because they're part of the same methyl group. Now, that's different than hydrogen C, and hydrogen C. Hydrogen Cs are all on the same methyl groups. They're all in the same chemical environment, but the two methyl groups are different. So we have HA and HC. Now, sometimes it's possible for a CH2 to provide unique chemical environments for the two hydrogens that are attached. But for the most part, we'll look at some examples, but for the most part, what we see is that, in fact, those hydrogens are in the same chemical environment too. So the H, for the most part, in many cases, H atoms on the same carbon are in the same environment. So we had 3 carbons. That's 3 landing sites for the various, it looks like 8 hydrogens. And so we would expect the number of 1H Nmr signals to be 3. 3 signals. Now what we could do is we could introduce some symmetry into the molecule to make things somewhat more interesting. If we have this molecule now, I've added an additional carbon to the molecule where we were working with before, along with the requisite number of hydrogens. That also introduces symmetry. We have bilateral symmetry in the molecule. What that does is that means the left side's the same as the right side. So if we have carbon A and carbon B and hydrogens B and B, hydrogens A, and A. Okay, due to symmetry, the left side's the same as the right side. So the first carbon that we encounter on the right side, carbon B, the first carbon is actually the same as carbon B. So I'm just going to label it B as well, along with both of the H's to also be B. And then the CH3 is in the same chemical environment, even though it's really far away, it's in the same chemical environment as the carbon A, because due to symmetry, they're both carbons that are attached to carbons that are attached to oxygens, for example. I mean, you have to kind of look at it a little bit more broadly than that, but I mean, that's the case. So what we would expect then is the C13 signals to be 2 and the 1H signals to be 2. It's terrible handwriting. Sorry about that. Okay. Now, interestingly, if we have a molecule like this, which could be drawn as either one of these two forms, we technically have bilateral symmetry, sure, but the symmetry is actually greater than that. Think about how many signals you would expect in the carbon and the hydrogen NMR spectra. Well, if you look at this, every carbon is in the same chemical environment. Every hydrogen is in the same chemical environment. So we have 1 and 1. Okay. What's important to note as you're looking for opportunities for symmetry is maybe you should think back to chirality in NMR, but if you have the opportunity to rotate the molecule to achieve bilateral symmetry, you will then get that corresponding number of signals in the NMR spectrum. So what I'm saying is if you can rotate a CC bond to get symmetry, you must use that symmetry to get the number of peaks. Oh boy. Or to determine, totally should have turned the page because I'm just going to turn the page in a second. All right. Plus, those are just words. We need to really look at an example. Okay, I'm going to turn the page. Let's do this. All right, let's say we've got this molecule here. Okay, we've got 6 carbons. So the issue is it's hard to tell if those 2 carbons are the same. I mean, they kind of look like they could be the same. Now, similarly, we could have the outside 2 carbons, we could have the inner 2 carbons, but how do we tell for sure? Let's do a free rotation about the central carbon atom. If we do that, we're at a molecule that looks like this, where now you can see we've got symmetry. And so for the number of signals, number of C13, that's going to equal 1, 2, 3. 3 signals. And just like the first example number of 1H, we'll see 3, 1 for each of the carbon atoms that are on either the left or the right side. We can break that symmetry fairly easily by introducing another group. So let's say we've got this molecule. And I'm just going to highlight that this does not have symmetry. So we have 1, 2, 3, 4, 5, 6 carbons. So the number of 13 C signals that we would expect is 6. None of them are in the same chemical environment. I know there are multiple CH2s and they will have similar chemical environments, but we can make the assumption that they would at some point be resolvable using some instrument. So I'm going to go ahead and call this 6. Now the 1H is a little bit interesting. Every hydrogen that's attached to the same carbon is in the same chemical environment. So if you have a CH2, both of the hydrogens are in the same chemical environment. Now, what we have here is sort of a, I will accept either answer if you put 6 or 7. 6, if you ignore the OH, as I mentioned last time, the OH will typically wash away. Now, that's an experimental result that we can overcome if we need to. And that's if, and so if you want to remember the OH, go ahead. This is just if somebody said, hey, here's hexanol, how many proton NMR shifts will I expect to see? You know, the 1H nucleus. If somebody said 6, if somebody said 7, conversely, if somebody said 6 or 7, all 3 of those possibilities are fine and correct answers. Okay. Now, so what we've learned from this is that the number of signals can actually be reduced due to symmetry, and the symmetry may not be apparent in one depiction, but due to conformational rotation, we can actually get to something that has multiple points of symmetry. And doing this allows us to, if we want to look at this more deeply, we could see that the free rotation of carbon-carbon single bonds is what allows all of the hydrogens within a methyl group to be within the same chemical environment. Now, that does have its limitations, though. For example, if I look at something like this, okay, cyclohexane, I would expect the number of 1H's to be 1 and the number of C13s to be 1. Okay. It's a lot like benzene, all right? Every carbon has 2 hydrogens, one's up, one's down, that sort of thing. But what if we do this? Now we've broken the symmetry of the molecule, and we get to a result that has many more carbons and hydrogens for the signals. I'm going to turn the page and we can look at that. So looking at this in more detail, the carbons is not too hard. I'm going to give the CH3 a wedge. It doesn't matter for the wedge or the dash. Those two are not different because this molecule has bilateral symmetry through it. But what's happened is when we do this, now the top and the bottom of the ring are different chemical environments. So the H's on either the top or the bottom will be different. Okay, so let's get the number of C13s out of the way. We would expect 1, 2, 3, 4, 5, 6, 7. There are 7 carbons. Now, it turns out that 7 and 3 and 4 and 6 are in the same chemical environment, so that's going to decrease this by 2. So we're at 5 signals. Okay. Now, what I'm saying about the 1H atom is that the top and bottom are different. So even if we have a hydrogen on the top and the hydrogen on the bottom of the same carbon, they will be in different chemical environments. These are now different from one another. Okay, so I'm going to give A to the CH3, B to the hydrogen at 2, C to the top one at 7, D to the bottom one at 7, E to the top one at 6, F to the bottom one, G and H. And then we actually, due to symmetry, the left and the right side are the same. And so we have E, F, because these, I'm just going to show this, these match and these match. It's just that the top and the bottom are different. So we have E, F, and then we're going to go C and D because the things on the left are the same as the things on the right. So now we count on our fingers, up to G. So A, B, C, D, E, F, G, H. We've got 8 signals. Just by introducing a methyl group, we get so many more signals because we destroyed the symmetry in our molecule. So determining the number of signals is really all about finding the symmetry within the molecule. But this is a really good first step because it tells you how many peaks you should expect. Now, once we know how many peaks, the next thing to look at is the chemical shift. I'm going to go through this super fast. This is just the labeled delta. This is the x-axis ppm value / position of a peak. Now, gleaning this is very helpful because this suggests the type of chemical environment that we have for our molecule. Okay, so if we had these two molecules that we were inspecting, benzene versus cyclohexane, so we have 1H signal for both of these. So the number of signals is not going to be a giveaway, but this one is at 7.2 parts per million, and this one's at 1.4 parts per million. Okay, so that is the chemical shift and why it's useful. You can see that chemical shift in conjugation with the number of signals is really telling about the structure of a molecule. But we can get even more insight if we consider the last two properties, and they kind of build in terms of complexity. So integration is the next attribute of NMR data that we want to look at. So I'm going to turn the page, go right to integration. So if you hear the word integration and you're having interesting flashbacks, maybe stressful flashbacks, in my case, integration to calculus 2, the concepts are the same. It's all about area under curves and that sort of thing from calculus, but the computers do the math for us. So the concept is, it's all about the concept. The computer will do the difficult, really difficult math. We'll do the super easy math. We won't actually apply any antiderivative techniques and that sort of thing ourselves. What this is this is the relative, this is now getting into the y-axis, the relative y-axis value for a peak. It gets the term integration because it's actually the area of of a peak, which a computer can do quite quickly, especially for some of the idealized Gaussian peaks that we see in NMR spectroscopy. Okay, now I said it was the concepts that matter here. So the important thing to remember here, this by the way, with integration, is one of the least complicated things that students make ultra complicated. It's actually fairly straightforward, especially if you get the number of signals. This will totally come pretty quickly. So signals or peaks can be made up of multiple 1H atoms and C13 atoms, but it doesn't work as well with C13 atoms. Okay, so let's take, for example, this molecule. All right, so what I want to do is focus on the number of 1H NMR signals. Why don't you pause the video and see if you can figure that out. The number of 1H NMR signals is, in this case, 2. All right, there are the HAs, and there's 3 HAs at every one of these carbons. And the A is just my label because it was the first hydrogen I encountered. So there's 3 at each of those carbons, and there's 3 carbons, all within the same chemical environment, by the way. So we have, this is kind of like what TMS looked like, where and there all 4 groups were the same. Here, all 3 groups are the same. And you can kind of prove that to yourself if you want to spend a little bit more time on that. But what we have here is we have 9 HA atoms. And then over at this carbon, I said, let's just focus on the 1H atoms. We have the HBs. Let me, just a second, my infant child is crying. I'm just gonna, okay, we're back. Let's see, sorry, my daughter woke up from her nap, needed some attention, rightfully so. Okay, so we have 2 1H NMR signals. We have 9 HA signals, and then we have 3 HB atoms, 9 HA atoms and 3 HB atoms. Okay, so what we do is we have to recognize that the signal for each of these is going to be, relatively speaking, reflective in the number of atoms that make up that signal. Here's what I'm trying to say. Let me just say it this way. With this ratio, the HA peak or signal will be 3 times larger, and that's determined by area, integrating the peak, determining the area under the signal's curve. Again, we don't have to actually do that, but what I just want you to gather is that HA will have a peak that is 3 times that of HB compared to HB. So let's say we go and we do the experiment. So we have chemical shift, which is in parts per million. And we have some y-axis, which up until now has been fairly arbitrary. And what we observe is that near 4.0, we see a peak, and at 1.0, we see a peak. So this is 4.0 parts per million, and this is 1.0 parts per million. Now what we do is we say, computer, integrate and the computer integrates. It likes to do math, right? I mean, we all do. So the peak for chemical shift 4.0 parts per million the integration is 150. And it's just some unit, okay? I mean, it's like units. It's 4.0 parts per million. It has 150 for its integration. I'm going to get rid of this delta because I think it just confuses things. Now, at 1.0 parts per million, the computer reports back that the integral is 450. Well, what do these 450 and 150 numbers mean? Well, the numbers themselves are useless, okay? It's the numbers relative to each other that are important. So let's turn the page. So the absolute integral numbers are not important. Rather, the relative values are useful. Okay, what am I saying? So the absolute values, 150 and 450. But if I compare 150 to 450, then it gets interesting. You can probably see this, but for the short peak, what I'm going to do is I'm going to take 150 and 450. Now I'm going to divide them by the lowest of the two. Okay, so I'm going to divide them by 150 because 150 is lower than 450. And what I get is this will always convert the lowest number to 1. Exactly. And then we get 450 divided by 3, divided by 150 is 3. So this is our integral values. So we have 1 and 3 for the integral values for these two signals, which is really interesting because that is the same ratio of the two hydrogen environments that we would have expected to see. Okay, that is when we come back to this molecule, we saw that we had 9 HAs and we had 3 HBs. So what we can then kind of infer from these integrals is that the 9 HAs corresponds to the tall peak, and the 3 HBs corresponds to the short peak. Now the tall peak was at 1.0 parts per million, and the short peak was at 4.0 parts per million. We can also gain some insight because this short peak, this CH3 directly attached to oxygen, all of these H's are in a chemical environment that's closer to an electronegative oxygen atom. Okay, so the integral can give you further insight that you can use with the number of peaks and the chemical shift to gain insight into what the structure is of the molecule. Now, one thing that people often ask when I go through this example is they say, why isn't the integral 9? There are 9 hydrogens. 9 HA hydrogens make up the signal at HA. Well, recall that what the computer is doing is it's just reading the data from the detector. It doesn't really know chemistry. It doesn't know what you put in it. It just knows that what you put in it gives 2 peaks. One is 3 times greater than the other. It's us that we have to then infer from that information, and perhaps using what we know about the molecular formula to say, okay, we're going to draw a molecule so that 3 of the CH3 groups are in the same chemical environment. That would allow us to account for 2 signals, one of which is 3 times greater than the other one. Let's look at another example. Let's say that alternatively, we see, and for your future self, I'm going to say ignoring multiplicity, which is complicating, which will complicate this example. Let's look at an isomer. Let's say that we see something like this. where at 3.0, we have a peak, and then at 1.1, we have another peak. That's, I didn't do a good job. I'm gonna make that a little bit taller. I'll give you it's a little bit taller. Okay. So I'm gonna go on the next page and I'm gonna try to analyze this. I'm gonna call this peak A and then peak B. Okay, so this is a similar molecule to before. Now, what I want to do is I want to emphasize that the experimental data, well, I think I called these A and B. If we have peak A, the experimental data isn't going to look anywhere near what you would expect like the number of hydrogens to be. So let's say that peak A is, make this interesting, let's go let's go 220. I want to get too cute. And then peak B has an integral of 330. Okay, so these are the integral values. Well, what you can do is you can do some math to show that the ratio of peak A to peak B, where you divide by a common denominator, which is 110. You don't need to know how to do this. I'm just trying to show you some experimental data, just to emphasize the computer doesn't know chemistry. Okay, so if we divide both of them by 110, we could say that peak A has an area of 2 relative to peak B, which is 3. This is now the useful number. And there are a lot of computer tricks that would just spit out 2 to 3. But if you actually like went in and did a manual integration of the peak, you would see some obscure number like 220. And then the other one would be 330. And it's not those numbers that matter. It's the relative ratio of those two numbers, which is 2 to 3. On a test, I'll give you like the integral is 2 and 3 and that sort of thing. Okay, so what could this correspond to? So you've got some possible molecules. Let's say the possible molecules are like these few, for instance. Well, let's make it this. Well, that doesn't work. Okay, we'll keep that. All right, so these are the possible molecules. Well, the answer, without lingering too much on to what is already a long lecture, is this. Because this molecule, which we said has a bilateral plane of symmetry, is going to have two types of H's. We have A, B, B, B. Now the ratio of HA to HB is going to equal 2 to 3. But the number of HAs is actually 6. And the number of HBs is actually 4. Okay, so trying to couple the experimental data with kind of just understanding the chemistry. Perhaps maybe I make this too complicated by stretching some pretty prominent examples already. The computer is going to give us a number. But what the integral is it just is a ratio of the area of the peaks based on the number of hydrogens that make up those peaks or that make up those signals. Okay, perhaps looking at some examples will solidify a lot of this for us. But integration is not something to worry too much about. As we practice, we'll see it start to click a little bit better. So with that, we'll end this lecture. In the next lecture, we'll look at the last attribute, which is the multiplicity. And I'll actually push the confirmations off until for a later lecture.